Welcome to this explainer. Okay, today we're unpacking the critical 2021 amendment to ISO 11439. Look, if you follow automotive engineering or alternative fuels, you already know that safely storing compressed natural gas in vehicles is an absolute structural and chemical engineering marvel. But the standards governing these high-pressure natural gas vehicle cylinders, they aren't static. They are constantly evolving. And this specific 2021 amendment is a massive leap forward. It redefines the extreme safety and testing standards that these cylinders must absolutely survive before they ever hit the road.
So here's how we're breaking down these updates today. We'll start with the new baseline, move into material thresholds, check out the enhanced pressure cycling tests, dive into Annex H on accelerated corrosion, and finally wrap up with the future of vehicle safety.
All right, Section 1, the new baseline, where we're refining some terminology.
This first update really hits the nail on the head when it comes to precision. They've officially swapped out the old language for exterior cylinder requirements, changing it from an acid environment test to a much more comprehensive environmental test. And, why does this actually matter? Well, out in the real world, these cylinders aren't just getting splashed with acid. They're dealing with a crazy cocktail of hazards: road salts, freezing moisture, random automotive fluids. So fixing this language ensures the testing actually matches the messy reality of the road, not just one isolated chemical threat.
Moving right along to Section 2, material thresholds. These are the hard limits.
Okay, the big takeaway here is the glass transition temperature of the resin material. Tested under ASTM D3418, it absolutely cannot dip below 102 degrees Celsius. To put that into perspective, the glass transition temp is the exact point where a hard, glassy polymer starts getting all soft and rubbery. Imagine a high-pressure cylinder wrapped in this composite resin, just baking in a sweltering engine bay, or parked over literally boiling asphalt in the dead of summer. That resin simply cannot be allowed to soften. So this hard 102-degree limit guarantees it holds its structural integrity even in the absolute worst heat waves.
Now, moving from the composite wrap to the internal steel components, the standard gets even stricter. Get this, the actual tensile strength cannot exceed the expected value by more than 5% on samples tested for sulfide stress cracking resistance. Now, you might be thinking, wait, isn't stronger steel a good thing? Well, actually no. In these highly calibrated pressure vessels, unexpected stiffness can actually create localized stress concentrations, leading to completely unexpected cracking under cyclic loading. So this tiny 5% maximum variance, it establishes a hyper-strict, totally unforgiving margin for error. It's all about ensuring perfect, predictable behavior.
Next up is Section 3, Enhanced Pressure Cycling Tests, where we simulate the extremes.
All right, here we are talking about some serious thermal and pressure whiplash. First, they drop the ambient temperature down to minus 40 degrees Celsius, or even lower. Then they hydrostatically pressurize the cylinder to a staggering 260 bar, which, by the way, is over 3,700 psi. Then they swing it completely the other way. The cylinder has to endure high temps of 65 degrees Celsius at 95% humidity, holding that massive pressure for 48 straight hours, just to test environmental fluid exposure. And, get this, to make sure absolutely no one is cutting corners, the standard explicitly demands digital logging of all these values every 6 seconds. If the system dips outside the parameters for even a moment, boom, that test cycle is completely thrown out.
The sheer brutality of the flaw testing is just fascinating. To prove these cylinders won't catastrophically blow up from a random scratch they picked up under a truck, testers must literally carve deep, specific longitudinal flaws right into the sidewall. Once it's intentionally compromised like that, they aggressively cycle the pressure from 0 all the way back up to 260 bar. And they do this repeatedly thousands of times to mimic the cylinder's entire design lifetime. It's an incredibly demanding physical proof of the built-in safety margins.
But amidst all this insanely strict testing, the amendment also drops in a highly pragmatic update. This newly added clause A27 defines the natural gas cycling test. This specifically evaluates the interface between the metal end boss and the plastic liner in Type 4 cylinders. Those are the fully composite ones, over 1,000 cycles. And here's the cool part. The clause clarifies that once a specific end boss design passes this rigorous interface test, it can actually be used in other cylinder designs without having to repeat this exact gauntlet all over again. It's a brilliant example of how standards can actually optimize engineering efficiency without sacrificing a single drop of safety.
Let's move on to Section 4, Annex H, which covers accelerated cyclic corrosion.
This brings us to what is probably the most significant functional addition in the whole 2021 amendment. Look at this flowchart. It maps out a relentless 24-hour cycle these cylinders have to endure to test their protective coatings. It starts at an ambient stage, then dynamically shifts into a 49 degrees Celsius humid stage, where moisture is just penetrating every microscopic pore, and then finishes off with a scorching 60-degree dry-off stage. And they repeat this cycle over and over again, up to 100 times, basically simulating years of harsh environmental exposure in just a matter of weeks.
And they're not just using plain water for this either. To pull off this corrosion test accurately, laboratories have to mix up this highly specific, really complex salt mist solution by combining sodium chloride, calcium chloride, and sodium bicarbonate in these exact, tiny percentages by mass. The lab simulates the precise chemistry of highly corrosive road salts and nasty environmental slush. Crucially, the standard requires them to apply enough of this spray to visibly rinse away the previous salt accumulation during those ambient stages. This makes sure the corrosion is happening actively and continuously, exactly like it would on the undercarriage of a truck blasting down the highway.
So after surviving those brutal corrosion cycles, the evaluation becomes highly forensic. They do this destructive tape pull test over sections of the cylinder that they intentionally scratched before the whole test even began. The resulting damage to that protective coating, which is known as scribe creepback, is strictly capped at 6 millimeters, no more. And furthermore, if you peel back the layers to look at the general liner metal underneath, any surface pitting absolutely cannot exceed 10% of the liner's overall wall thickness.
And as we can see here, the threshold gets even tighter at the cylinder neck region. This area is structurally vital, right? It's where the valves attach, and it's where immense physical forces converge. Because of that, allowable pitting corrosion in this specific zone is strictly capped at a maximum of 5% of the neck wall thickness. There's absolutely no room for structural decay where it matters the most.
Finally, that brings us to Section 5, the future of vehicle safety.
As we wrap up this explainer, it's really vital to step back and just look at the big picture impact here. Every single new rule we've talked about, from precisely mapping out salt spray percentages to mandating data logs every 6 seconds, it all represents the collective, hard-earned knowledge of global engineering committees. So I'll leave you with this thought to ponder. When a standard forces manufacturers to account for a mere 5% variance in steel cracking or perfectly calibrate a 102-degree resin melting point, how many lives are being quietly, invisibly saved on the road every single day? It's a powerful testament to the fact that true safety isn't an accident, it's by design. Thanks for joining me to explore the vital mechanics of ISO 1149, and keep questioning how the world is built around you.